The objective today is to explain what the Intel manual says about binary coded decimal integers, aka BCD. And this builds nicely off our last video where we talked about packed data types, but in this case we're going to look at packed BCD integers. Though I guess all BCDs are integers, I mean binary coded decimal integers, that is. Up here we see really regular integers, and we can have them at a byte at a time. So this first byte could show the number 0 all the way up to 255, and then this next byte can show the exact same range of numbers. Or we can go with bigger numbers when we're at the word size level. And this is true for the floating point data types, and then this whole SIMD concept, this is usually done in 128 bits at a time. So to start this part of the Intel manual though, I should actually just start with a picture. Picture's worth 1,000 words. So right here we have our regular binary numbers, 0 through 9, and those look not surprising, okay? We have the ones place and then the 2s and the 4. So 1 plus 4 is 5. That makes sense. And if we look at the BCD column here, these are binary coded decimals in a single byte here. Everything is the same up until the number 10 here. That's when things get crazy. So the way you make a 10 in regular binary is you take a 2 and you add it to an 8, and that's 10. So 1, 0, 1, 0. And of course these are all zeros. But if we wanted a binary code decimal something, well then we could have a 1 right here, and these are all zeros, and thus, do you get it? It's a 10, all because of this concept of a binary coded decimal. And the Intel manual says as much. It says that BCDs are unsigned, so they can only be positive, and they are unsigned 4-bit integers with valid values ranging from 0 to 9. So we're very limited, huh? So there's your first question. How many bits is a BCD integer made of? And we're going to answer it by saying something like 4 bits at a time. Now, the IA32 architecture defines operations on BCD integers located in one or more general-purpose registers or in one or more x87 FPU registers. So simple question there, where can you find BCDs? Well, they supply us a picture here, but I think the one I showed you might have been a better one to look at. But I do like that they go down here and go with 80 bits at a time to show us that we're still at 4 bits for one digit, and if we have 80 bits here, we can have a really large number. Well, relatively speaking, that is. It's actually a smaller number than we could demonstrate using regular binary, so I'm really lost as to why this would be helpful, but maybe the manual will clue us in here in a little bit. When operating on BCD integers and general-purpose registers, the BCD values can be unpacked, 1 BCD digit per byte, or packed, so you can have 2 BCD digits per byte. Oh, that makes a lot of sense, and so the X is just the padding. But if we pack it, then we don't use padding. Whatever number is here, right, 0 through 9, was it? Well, it has to be. If I have all ones, I have the number 15, right? 8 plus 4 is 12, plus 2 is 14, 15, yeah. But I can't have a 15. Let me go back to that chart and see if they show us like really huge numbers. Well, no, they stop at 20, so. Alright, let me focus on the manual, and then in another video maybe I could dig deeper into some research here. They go on to say that the value of an unpacked BCD integer is the binary value of the lower half byte, so bits 0 through 3. The high half byte, bits 4 through 7, can be any value during addition and subtraction, but must be 0 during multiplication and division. Packed BCD integers allow 2 BCD digits to be contained in 1 byte. And here the digit in the high half byte is more significant than the digit in the low half byte. So that makes sense. We're still going with that same pattern. The same pattern we use with binary numbers, that is. So if I have 1001, this one right here is the least significant. This is the ones place. They're saying the same is true Let's say I have the number 0001 and then a space. So there we go. They're saying in a BCD digit, this is the least significant. So this being a 1, 2, 4, 8. So 8 plus 1 is 9. So they're saying that the 9 is the least significant. It's in the ones place. And then that 1 right up here is the most significant. So that's the number 19. So just for a check of understanding here, I'll ask, how do you make the number 20? And I have an example right here for you to get started with. Oh, and be sure that you're doing it in this new BCD format that we are learning about. Alright, so when operating on BCD integers in x87 FPU data registers, BCD values are packed in an 80-bit format and referred to as decimal integers. Wow, so when you're working with the floating point processing unit, you're using the whole 80 bits right there. In this format, the first 9 bytes hold 18 BCD digits, 2 digits per byte. Oh, that's so key. So that's going back to what I was saying. If I have like all ones, we know that is normally 15. So if I go over here and I add another set of all ones, my question is, does that make this not binary, but this decimal number? Oh, but since I see it right here saying there are only 2 digits per byte, that tells me that like, no, we can't do that. Sad face, okay? We cannot create BCD, or we cannot create decimal numbers that way. The least significant digit is contained in the lower half byte, or byte 0, and the most significant digit is contained in the upper byte of byte 9. Man, they are repeating themselves right there, I think. Where's the editor for this? Well, the most significant bit of byte 10 contains the sign bit 0, which means it's a positive number, and 1 will be for negative. Bits 0 through 6 of byte 10 are don't care bits. That is new. That's kind of cool. So where are the don't care bits? And we can see that up here. So 78 through 72 is the don't care bits. Maybe I should say 72 to 78. Or you could even say right here, like bits 0 through 6 of byte 10. Well, negative decimal integers are not stored in 2's complement form. Whoa, that's mind-blowing. They are distinguished from positive decimal integers only by the sign bit. The range of decimal integers that can be encoded in this format is negative 10 to the 18th plus 1, all the way to 10 to the 18th minus 1. So at this point in the manual, I'm thinking this BCD style of storing data is like the style I would have used if I was just making this up on my own. So like everything in tech, I'm sure there's some benefits and drawbacks to this style. Well, we're almost done here. It says that the decimal integer format exists in memory only, and when a decimal integer is loaded in an x87 FPU data register, it is automatically converted to the double extended precision floating point format. Everything goes back to normal when we're looking at floating points, it seems like. Well, all decimal integers are exactly representable in double extended precision format. Man, I cannot speak. But maybe that'll make it more memorable. That double extended precision format is like the golden spot for BCDs. Well, anyways, here is a relatively unhelpful table, just like usual, that Intel likes to give us. But I did notice this difference when I was trying to analyze them, like the whole column is all zeros when we're looking at these packed decimal integer encodings. And yes, this is like a different encoding, right? So I think this part of the table, it says table 44 gives the possible encodings of value in the decimal integer data type. So it looks like this part of the table, this is just regular numbers. But then to indicate, right, BCD indicator, if these bits are all ones, we have ourselves a packed BCD indefinite. So the last sentence says that the packed BCD integer indefinite encoding, so that's all ones, right? These F's right here is all ones. And then there's this letter C. Okay, so they're going to make me break this down. So the one F here is these 4, and then there's another 4, and then another 4, so we're up to 3 of them. Here's the 4th one, so yep, there's 4. So this right here is the C, and then yep, everything is 0 after that, and right here, everything is 0. And the H just means hexadecimal, right? So the packed BCD integer indefinite encoding is stored by the FP or FBSTP instruction in response to a masked floating point invalid operation exception. That might be worth writing down right there. And if we're talking about masking, that is a similar concept in subnetting, or if you ever use the umask command. Usually when you're looking at a mask, we're looking at an AND gate or some sort of logic gate being used. Like I said, usually an AND one. So let's get some questions down. So I'm trying to simplify here. Which instruction stores BCD integers? And that is this FBSTP instruction. And I'm not really sure what to write for a question on the second one, except maybe a genuine one. So maybe I would say, like, what is a masked floating point invalid operation exception? But I need to spell it correctly. And with that crazy, extreme, but genuine question, I think we're at the end of our video. Last sentence, attempting to load this value with the FBLD instruction produces an undefined result. So I assume an undefined result is a bad thing, so I could ask the question like, what happens when you try to load this value with FBLD? And I'm also like wondering, what is FBLD? But maybe we'll find out later in the manual. As always, thanks for watching.